Picking up where we left off last week, we were just getting into this topic of web applications. And where I left it was this kind of hackneyed interpretation of basic web application architecture. And the main point, the main takeaway is that when we talk about web applications, we're actually talking about several different things. And that's why it's potentially an interesting topic to explore a little bit deeper. There is more than just the actual piece of software on the client we would refer to as the web application. There are potential issues involved with the server itself or back-end servers or on the database servers itself. So, and all those things kind of get thrown together in one big pot and all sort of referred to as web application security. So they're all connected to each other, but we're kind of going to be jumping from one part of this diagram to another as we go here. To do that, I think it's important to just do some very brief introduction to what we're talking about with regards to the application layer. We know this, I think, and I'm just reviewing this just to make sure we're all in the same frame of reference. When we talk about HTTP, Hypertext Transfer Protocol, that is still the standard method for communication from on that left-hand side of that diagram between the web server itself and the client looking to access it. It has been around for a very long time now, but it has undergone various revisions beyond just the introduction of HTTPS, which is the one that's using either transport layer security or secure sockets layer. You can think of it as HTTP with security, which is effectively what it is, as well as more recent innovations that we're looking to make different trade-offs in terms of performance and expressiveness of the protocol. I actually added an asterisk there when I said HTTP2 is the most common version in use today. That it seems to be a rapidly changing facts on the ground. That was the case, I think, when I put the slide together this past summer. It's maybe very close to 50-50 now at this point. So with this HTTP3, which is using, instead of TCP, it's using this QUIC protocol, which is not really an acronym, but you can think of it as quick UDP internet connection using multiple parallel UDP streams versus just a single TCP stream. That has had a significant uptake even in the last calendar year. So going from sort of this newly introduced thing just a couple of years ago to now, since, for all of Meta's products, for example, it's all using QUIC. That adds up to a very large percentage of internet traffic, and so those numbers are changing quite rapidly. That's actually, when I say most common, that's actually a sort of difficult thing to truly measure. Are you talking just total number of bytes, total number of clients, total number of web servers? But it's growing, and that will eventually become the thing we would study in more detail when looking at HTTP versus looking at just HTTP over TCP over IP. The fortunate aspect is it's close enough to TCP that we don't lose a lot of generality by just talking about HTTP more generally and not worrying about the underlying network stack underneath it, because they all follow, including HTTP3, the same communication approach, which is the so-called client-server model, right? This is true of a lot of networking applications where your client is making requests of a server. In this case, the client is going to be your web browser or mobile application, and that server is going to be a web server. For HTTP2, the client will be making TCP connections to that web server, generally, although not exclusively, port 80 for HTTP and port 443 for HTTPS. And then there's just going to be a series of those HTTP requests and responses for all the various aspects of the data that needs to be transferred related to that website. All the HTML, all the images, all the style information, all the various locally executed source that are associated with that web page that is then interpreted and rendered locally by the client. And those requests are encoded by name using so-called uniform resource locators, or URLs. Question? They're complementary things, right? So HTTPS is really referring to how the traffic is getting encrypted before it's getting sent out, but then it's ultimately just the same thing underneath the hood. The actual syntax of the resulting plain text protocol is exactly the same thing underneath the hood. Just a couple well-known people. There's a lot of well-known people we could highlight. Tim Berners-Lee, who is the inventor of the World Wide Web, HTML, HTTP, and URL. So we owe a lot to him and his generation building it. I wanted to also highlight Mark Andreessen, who you may know in other contexts these days, but co-creator of the first widely used web browser, and he was born in Iowa. Do we know what the first widely used web browser was called? This is before your time. It makes me feel old, and that's okay. It's called Mosaic, which then was commercialized into a company known as Netscape. Has anyone here ever used Netscape before? I'm getting old. I'm feeling it. That's okay. You may know Netscape by its like kind of open sourced name. That when the company itself realized they couldn't really compete, they said, "Here's the source code. Somebody else make something of this," and it became widely used as Mozilla. Have you used Mozilla or Firefox? That's all that same, all from that same exact code base. I had to look it up. Mozilla was a portmanteau of Mosaic and Godzilla. Still doesn't really make a lot of sense, but that's why they called it Mozilla. That organization is still around today. Many of you might be using the Firefox web browser. All started back in that era with that research project in Mosaic web browser. Sometimes when we look at protocols like this, it can seem sort of purely abstract. And so I want to make that clear that, of course, networking stacks are an abstraction, right? We have application layer over TCP, over IP, over the underlying physical layer underneath it. But at the same time, it's not really a pure abstraction. When I talk about a typical HTTP request and response here, I'm actually being quite literal in the sense of in whatever TCP IP packets that are being constructed, there is some payload, right? There's some actual data we are interested in sending, and quite literally, you're sending this, or that is an example of a valid thing that's getting encoded. Literally, the ASCII text or the ASCII bytes corresponding to those strings of text are what are getting sent. So it is an abstraction in the sense of, yes, there's ones and zeros that are getting put together into IP packets and sent over an Ethernet connection or over Wi-Fi, but really, this is actually what's getting processed at that application layer in our web applications. And while we don't really need to become fully fluent in HTTP to appreciate this topic, it shouldn't stay a complete mystery to us. I said this is typical. This is not an exhaustive example, but for a typical HTTP request and response, you will have to start off with a method associated with it. Method, you can think of this as the command type, of which there are actually several different options, but you can get pretty far with your understanding with just an appreciation of just both get, which is a request to retrieve information, literally, get me this information, and the flip side of that is called post. Send this information to the server. So that's literally those 3 bytes. Get GET, get sent. That is the request that is made. Then there is the actual scheme. That's your HTTP or HTTPS. Depending on the server, there are other schemes that are valid, but HTTP and HTTPS are sufficient for our purposes. There's the name of the server. So we're familiar with domain names and what they look like. There is optionally the port associated with that request. I mentioned HTTP is over port 80. If you don't specify that, effectively a port 80 gets added to that, but there's all sorts of purposes for which we want something other than the default port. We have the actual path that we're then interested in this case, just something at the root called test.html. And then optionally, you may have some additional query string associated with that. What happens with that string is sort of site and server dependent, but there's a standard syntax for providing a query string where you're basically providing variable and value pairs. We have a variable we're passing or parameter called name, which we're saying Steve, and age equals 44. And then you have the various headers associated with this request. The host is actually optional, but you can provide the host that we're interested in. You then would provide potentially optionally a user agent. And so this does actually provide an attempt to fingerprint some aspect of your machine. It could be the case that different web browsers, different web servers would want to provide different styles of content depending on the machine that's attempting to connect to it. That used to be a lot more common than it is now, but it is still the case that on certain websites you can receive different content if you're telling it that you're running on Mac OS versus Windows, or that if you're using Chrome versus Mozilla Firefox here. That is the request. So that is the get me that web page with these parameters, with this sort of request-related header information associated with it. And then for that request, there will be some nature of a response. This is kind of intentionally abbreviated here, but part of that response would be that status code. So the first thing you'll hear back is you made an HTTP 1.1 request and you're getting status code 200, of which there's a pretty long list of documented potential status codes, but that range with that first digit is pretty sufficient, I think, for your understanding that if you get something that starts with a 2, you had a successful request. 200 means okay, we got an okay request. There's all sorts of different errors, either at the client or on the server, which you can check, and the client does check to see if something has gone wrong. And then there's the actual content with that request. You requested that test.html on that server, and then there's whatever happened to be within that HTML on the server is what gets returned back to you. That is our HTTP request and response. You may be thinking that as, yes, of course I know that. I go to a website, I type in the URL in my web browser, I get this HTML back, and that is true. That is also using that mechanism. But effectively all of our web applications, whether they appear to be a web browser in which one enters in manually created URLs or not, are effectively using this mechanism to do that bidirectional communication. We are requesting resources via these URLs over HTTP. We're getting resources back out. In terms of attacking the server itself, I mentioned this last week, but just to reiterate, a web server is just a networked computer like anything else we've been interested in. It is a computer connected to a network, running a service, opening up a particular port to run that service. So really, in terms of attacking a web server, at least in the conceptual phase, it doesn't need to follow any different methodology than what we've already been covering. So reconnaissance, scanning, and enumeration, all the things that at least for some certain configurations we kind of know how to do. Another approach that's unique to web servers is there's oftentimes the ability to analyze what content is being hosted by that website by mirroring, by making a local copy of the website versus having to make lots of remote requests to that website. It's actually something that has gotten more difficult to do, not easier to do. As web features have gotten more advanced, as the kind of programmability of websites has gotten more advanced, as the type of things that are running beyond the front end of the website have gotten more advanced, it's actually gotten a little bit more difficult to do that than it used to. Back in the day where all we cared about was grabbing sort of maybe the static HTML from a website, we would just use a utility like wget. Wget is a very well-known, well-established command line utility that works on very simple websites. In practice, though, there's a more complicated interaction between the client and the website, even to render a single static-looking web page. And so a single wget request, and we can try it here on our own department's website, is kind of limited in terms of what it's capable of doing. What you tend to need these days are server agents that act as if it is a user attempting to access that web page and interacting with the web page to be able to get what that content of that web page would correspond to. And there are tools to do that. They're not as straightforward and maybe as clean to use as wget, but that's at least a starting point. So I can open up just a command line here and call wget, if you guys can see that, on our department's website. And here I'm just requesting like whatever the first response, default response is. So I said it could take a long time if you were trying to recursively explore every link on our website and grab every file that's possibly located in all those sites. But here I'm just saying, effectively, give me whatever the default response is from that website. And it did say that we got index.html. You actually can see some aspects of that kind of HTTP protocol here. We see the 200 OK response. We see port 443. This is using HTTPS, and I think by default almost everything is doing so these days. And we get our index.html back out, and we can take a look at our index.html to see what it looks like. Something seems terribly wrong. Let's take a look at the file. let's make sure that got put in the right place. Okay, so wget, let's do -m. Now we go. Well, now we're grabbing lots of things. I had wanted to show the site actually loading. Let's load it up one more time here. And now it seems like it is loading. It really seems to be stuck. It's a piece of software that's attempting to do all these HTTP requests. You can actually take a look and attempt to view all those different requests. I wasn't necessarily prepared to do that here today, which should give you a feel for what exactly is going on and why it's still stuck and still loading here. Again, you can tell that it's not the actual website located on ece.iastate.edu because you can look at the URL that's up there and it's just the local file on my system. And it looks like it was slow. It looks like it's completed now. Well, probably because the website wasn't meant to be rendered via a locally downloaded file. It's also requesting all these either relative paths or things that are limited in terms of which websites, which domains can access those resources. So as we're attempting to load the website, we're seeing lots of errors of blocked by client, file not found, and all those can take a long time for it to fail in terms of the actual loading of the website. So we do have it though. It just took a little bit longer than I would have expected. And we have effectively a local copy of the website, all the source code associated with that website. We can see exactly what's happening underneath the hood. In terms of those errors, it's also possible our website has errors in it. I mean, that wouldn't shock me either. So this is now loading the correct version of the website. Yeah, so in fact, there's some issues with regards to the source code of our website itself. So that was grabbing it correctly, and there's just, like any other piece of software, there are various frameworks in use, maybe not entirely properly at all places, and it's maybe intentionally, maybe accidentally giving me a few errors as it's attempting to load. I think if you look at most modern websites and you load the whole thing and you inspect what's happening, you'll find there's a lot of, not trial and error, but a lot of things that are failing gracefully, but still providing you with a reasonable output there. So, okay, so again though, my takeaway from this that I want you to remember is it is a web server. There is a server, and we looked at how we would grab some of that information, how we would do the reconnaissance. Ultimately, there's an IP address somewhere hosting that website. It is our web server. And in terms of attacking that particular machine, it's really not any different than attempting to figure out more information about any other machine. We probably know a little bit already by default. It's probably just a web server and not also doing several other things, although that sometimes is the case. It is just a web server, so we can do that kind of fingerprinting style of analysis where we can learn what version of web server software it's using. Are there known vulnerabilities associated with it? Are there existing databases of exploits that we can play around with? So the same kind of methodology can follow. The only other add-on to that, why I kind of stumbled through running wget on it, is sometimes mirroring the website locally to your own system, your own machine, can itself provide additional insights as to what is going on with the web application itself. In terms of the fingerprinting, we did a little bit of that earlier in the semester, in which Nmap was able to determine that. Sometimes it actually is provided in the header information itself, what the actual web server is. We looked at Netcraft in a slightly different context, but part of their mission is to attempt to basically fingerprint the entire World Wide Web. And so they do provide these kind of rolling statistics of, amongst other things, which web servers are most commonly in use. And this is something of a timeline of it. The caveat I added here is kind of similar to the other one. Just like knowing the exact nature of all HTTP traffic out there is kind of a best guess and estimate. It's not a knowable fact necessarily. It really depends on methodology. So I say this is just my caveat to you. Don't go repeating that Nginx is 22% of the web servers out there. That may be roughly true. It may be off by some certain amount. Different methodologies and different websites that use different methodologies report different numbers for that. But you can see something of an interesting historical trend in terms of what was considered the most popular method of hosting websites then and now. The color scheme could be a little bit better in terms of differentiating a couple of those bars there. There was certainly a time when you really effectively had two different choices of web browser. You could use Apache as kind of the open source version, or one of a few different Microsoft variants for the sort of Windows hosted version. And it does seem that for the most part, people using Microsoft to host websites is kind of dropping over time here. But this other includes Kestrel, for example, which is a Microsoft product for hosting ASP.NET sites. So that also involves Microsoft technology. You see kind of Apache is still a factor, but now there's these other both open source and proprietary variants that people are using. So you do see a lot of Nginx. You do see OpenResty, which is effectively just Nginx, but support for certain interpreted languages on top of that. You certainly see a lot of Cloudflare. That is a very hard thing to estimate. Cloudflare is acting as effectively a front end for the entire internet and more of the entire internet. So you may be accessing Cloudflare even if that isn't kind of the default for a particular website. That becomes a very difficult thing to measure. But this is just the kind of different things one would run into. And depending on versions, there may or may not be various vulnerabilities that we would be interested in exploring further. Historically, there are some very fun examples of web server vulnerability and exploits. Beyond just the existing types of attacks we've already covered, we also separately sometimes have to worry, specifically in the context of websites and web servers, we have to worry about denial of service or distributed denial of service. The idea that by kind of creating as many spurious or illegitimate HTTP requests, those are provided to the server, those are sent to the server in order to kind of slow down legitimate requests or just otherwise overwhelm the server. We talked a little bit about compromising DNS to redirect to different websites. And then a couple examples that are historically famous, but are still actually an issue that I wouldn't say is solved, is this issue of sort of directory traversal attacks. We do a silly version of that in the lab, but it's not that far off from what these attacks look like in practice. That'll be in Lab 6, where we're taking a legitimate URL and attempt to access other system files and resources. Pretty famous example, and back in the early 2000s, it was kind of just expected that every few weeks or months, the entire World Wide Web would be kind of vulnerable to something. And that was just kind of an expected day-to-day occurrence. You know, you'd wake up, you open up a web browser, oh, well, this website got hacked today. And it wouldn't be that shocking because there was just less of a focus on security, less of an understanding of the things we've started to kind of provide a more rigorous methodology about these days, both on the software development side as well as on kind of the security monitoring side. But the Microsoft IIS, Internet Information Services and Server, was vulnerable to both Code Red and NIMDA. You may have heard of either, you may have heard of neither of them, but they both cause very widespread outages. And I list the CWE associated with path traversal here, but it was really more than that. But in terms of kind of the initial entry point for what these worms were effectively doing, it looked kind of like this. So as part of our HTTP requests, we have this GET, which is on this server, maybe using this port or this mode, give me this resource, index.html. Well, of course, it could also traverse directories as associated with that. And while we are gaining a little bit of comfort with our knowledge of kind of relative paths in Windows and Linux, let me just briefly interpret what this is attempting to do, right? It's a GET request on some website, starting in this directory, which presumably is an allowed directory that we want the user to be able to access, .. I get my forwards and backs, but for web services, it should work right away. It says go up a directory, go up another directory, now grab that file. IIS, even in its like version 3.0 incarnation, could detect that was happening. That was not supposed to be allowed. We want people to be allowed to access scripts and whatever, JavaScript or whatever is located here. We don't want them to go just arbitrary up an arbitrary number of directories. Again, ultimately, this web server is running on a machine. This IIS software is running on a machine as part of an environment in which it's starting in some directory, and then the rest of the system is still accessible relative to that starting directory. So for the very basic kind of trivial attempts, it could detect it, but not detect very, very slightly more devious Unicode or just encoding attacks in which by using 255C got decoded just as C, which is the backslash. Give me this directory and give me command.exe relative to where that web server is executing from. So from there, you don't necessarily have a shell just by running a local command on the machine. That's not the same as the reverse shell we talked about 2 weeks ago. But once you can run command.exe on that server, there just needs to be some sort of other vulnerability in the system that you can take advantage of. This is kind of related to last week's topic, which was our privilege escalation, right? As a user of a website, as a client connecting to the web application, I need to have basically the permissions of that web server. I need to be able to access resources on the server, on the machine, that web server piece of software has access to. I need to be able to have access to this whatever scripts or index.html or whatever files are associated with the website. That is not a vulnerability, that is just required sort of public-facing permissions that all users of the web application need to be able to have. This then would represent potentially some sort of horizontal privilege escalation, right? I had access to this, now via what seems very trivial to us today in 2024, via this bug that allows kind of arbitrary relative path traversal, I now have access to whatever command.exe is capable of doing. That's still probably a horizontal privilege escalation in that it's still whatever privileges the web server process has, I now have access to, but now I can do more than just grab the files that are expected I'm supposed to have access to. From there, you're basically acting as a local user on that web server, and if there happens to be anything else wrong with that particular piece of Microsoft software, you would then potentially be able to have vertical privilege escalation, right? If there's any other vulnerability of the types we were talking about last week, then from this command, you can do all sorts of things, of which in that era, there was a new one discovered every couple of weeks to give yourself additional permissions on that server. And in terms of code red, while it's actually not super trivial to understand what's happening with what additional vulnerabilities were being exploited here, but you can kind of sort of squint at that and see, well, and squinting at is all I want you to do for this. It seems to be buffering a lot of arbitrary data that it's sending. And then it appears to be some sequence of bytes that it's sending afterwards. We do a little bit of this in the lab, although we just download it and don't really look underneath the hood of what's happening. This is then effectively a shell code that's being provided here. We have some buffer in the web service. By sending just enough data, we're overflowing that buffer. What we then provide then is the bad stuff. It's effectively corresponding to presumably Intel x86 assembly instructions, what the corresponding byte code would be for that, machine code would be for that. So from path directory traversal vulnerability to some other vulnerability that happens to be on the system, you get a vulnerability that can then spread potentially across the entire World Wide Web. That's the case for code red. That's the case for the NIMDA worm as well. They were all, in that era, they all felt kind of similar, that IIS was the server. There was some fundamental vulnerability in Microsoft in some system service, and it was relatively easy to exploit because, again, the whole point of a web server is you want it to be available to users across the whole world, right? You want people to be able to access that website. And so there was not an uncommon thing in 2001. You'd wake up, you go to a website and find that it says something inappropriate or has been just completely taken down back in that era. It's less common now, but really when it happens, it tends to be more widespread these days. So that's really the limit of all we need to talk about with web server security. It is a server, it's a piece of software, same philosophy, the same hacking methodology we've been talking about all semester applies for that as well. Specifically about the application, the software potentially running both on the server or on the back end or on the client. As discussed, there is a lot of overlap between just software security and in general, and web application specific, web application security in specific, because ultimately, a web application is just a piece of software. So while we call this out as a separate topic, ultimately it is just a piece of software. So the type of common weakness enumerations we were talking about um, are totally valid. Where there's some value in looking at web application software separately, well, first off, there's some aspects that make it more critical. And then we can also kind of focus on the solution space as well a bit more by looking at just web applications. First aspect is complexity. There's a lot of complex software in the world, but in modern web stacks, there is a lot going on. And there is framework upon framework upon framework. You, as the developer, are writing 3 lines of code, and underneath that is getting generated 50,000 lines of code that you don't even necessarily see, and you certainly don't necessarily debug. Connectivity is what makes web applications different than just software in general. By design, we have a web application. Usually the goal is to have as many people accessing a web application as possible. Extensibility at all layers is also a potential complexity here as well. This is a more modern feature, but the idea is that new functionality can be added at multiple layers as part of the design paradigm. But then, while there's all sorts of modern web frameworks, we were talking about HTTP, right? We're talking about 1980s technology. We're talking being built upon TCP/IP. We're talking about even older technology than that. So while we have all these sort of modern web frameworks, it is kind of built upon frameworks upon frameworks upon frameworks developed potentially decades ago with kind of backwards compatibility considered essential. Note that this is true of a lot of software, but it's especially true of web applications. This is another XKCD about all modern digital infrastructure, and at least in part resting on a project some random person in Nebraska has been thanklessly maintaining since 2003. That was meant to be kind of humorous when there was really big issues with OpenSSL a number of years ago, which was a very popular, and I just provide the links. We won't read through the whole thing here, which was a very commonly used open source piece of software to secure the HTTPS side of things, to secure the communication between web server and web client. And it was effectively ubiquitous in that at that era, almost all web implementations were using that open source software as a starting point for it. And it turned out that there was, again, what would look to us in hindsight a very obvious looking bug, but was hidden away for many, many years. And it was a pretty bad one in terms of the resulting security of the SSL layer in our HTTPS. It turns out it really was 2 guys. 2 guys who, as mostly as sort of for passion project, they were getting paid for doing other things, were the ones who had been maintaining this piece of software over a period of years and years and years. So another way to look at that antiquated paradigms is web application security is relevant because while there is a lot of complexity, it's also built upon a lot of ultimately fragile things that have been developed piecemeal over a period of decades. And it's not ever as simple as saying, let's just all start everything over from scratch. That has proven to be a very difficult thing to do just from a practical consideration. And then inadequate testing is also an aspect of this. There's still kind of a developing field of software testing in general, but for web application testing, it's something that is more art than science, and understanding truly how one can do security testing for web applications is something that we're still trying to explore and develop as a security community. And that is still why to this day, Google can release a new web application and they wind up just having bug bounties associated with it. As opposed to being able to prove to themselves that they have sufficiently secured the application, they say, well, it could be breakable. Let's offer people money to break it for us, and then we can fix it in that way. That's not really an adequate way to do things. I don't consider that a proper approach to doing things, but it's sort of a necessary reality on the ground that it can be more challenging to exhaustively test a web application than a more arbitrary piece of software that can be tested in isolation. This brings us to OWASP, which could have also been the title for this whole topic. That's the Open Web Application Security Project. It's a nonprofit that provides that analysis in the field of web application security. It also does IoT security, so we'll talk about that a little bit later in the semester. They're mostly known for the OWASP Top 10. That's the 10 most critical web application security flaws. It's based on surveys. So it's based on surveys of industry professionals. So it's a little bit of, for those actively working in the field, let us know what you are seeing, what is relevant to you in the field right now, and those are then all collated together and prioritized in one way, shape, or form. In some sense, it is very similar in nature to the CWE system we've been referring back to this semester, because the focus is on the root cause of the security flaw. In another sense, it's more useful in that by focusing only on web application security, the type of security flaws that are talked about in the OWASP Top 10 are, I think, a little bit more actionable than just saying, well, I should avoid buffer overflows. That's good to know. But now in the OWASP, we can talk specifically about the web application and what kind of things can hopefully be prevented by design or detected post-implementation to see if you have those vulnerabilities or not. So it's considered more of a guiding document for those who are developing web application, or more frequently, I would say, web application frameworks these days. And it is considered something of that standard for if you're building a new web application, more likely a web application framework. What things do you have to look out for? What are known problems that you should be dealing with in the development of your web application? So it's a top 10. I don't think it necessarily means, although they are ranked, that you should only worry about 1, 2, 3, 4, 5, and don't worry as much about 8, 9, and 10. They kind of alternate between much more kind of CWE related sort of failures and very specific things that are really only going to be the case for web applications, like server-side request forgeries. Last version was in 2021. It's due pretty soon here for a 2024-2025 update. Most likely, though, looking at past versions, it'll, for the most part, involve some reshuffling and maybe 1 or 2 new entries. So we don't lose a lot of modernness of the list by looking at the 2021 version. It gives us a pretty good feel for what is still today considered most relevant for web application security. So for each of these, there's kind of a high-level description of what the basic vulnerability is, as well as an attempt to provide some specifics of what that would look like in practice, and then finally, what one can do at either the framework development layer or the web application layer to say, here's how I look for this, here's how I potentially prevent this. For some of these, I think it's more obvious than others. So we'll get through the first 3 or 4 today, and then we'll finish up the list after our quiz on Thursday. So again, a couple of these could also just be CWEs, right? These are weaknesses in software more generally, but they're seen as prevalent and relevant and important for web applications in particular. So the first one, AO1, is referred to as broken access control. We have been working with broken access control all semester. For the most part, we've been referring to kind of operating system defined and enforced sort of traditional user access control and looking at permissions on files and things like that. This is related to, but not exactly that. The idea is you have access control, you have some policies and some enforcement mechanism limiting what particular users are permitted to do. And broken then in this context means somebody's able to do something they weren't expected to do. So in some sense, that's a little too all-encompassing what it means to have broken access control. It means that somebody has access to something they were not intended to have access to. So the type of vulnerabilities that are under that fairly broad umbrella would be just in general, violation of the principle of least privilege, which is the idea that I'm going to start with a new category of user or a new user. By default, I want them to be able to do as little as possible, or effectively, I want them to be able to do nothing. I want them to have 0 permissions or 0 access in my web application. I only add what I believe is absolutely necessary for them to be able to function as expected within my web application. That is least privilege, or the same as deny by default. By default, we have a new user, they should be allowed to do nothing. And we only add back in what they need. That is the converse of allow by default. By default, we have a new user, they're allowed to do everything, and we have to go in and remove the access that they're actually not supposed to have. Things like then bypassing access control checks by just modifying the URL or modifying API requests. Again, I think that's a category of vulnerability that when we look at it, we would say to ourselves, well, I would never allow such a thing to happen. But kind of by default, if one doesn't take care in the design of their web application, that is effectively allowed by default. And then things like also then allowing users to tamper with metadata and not having good mechanisms to check whether or not that has happened. That tends to be related to other vulnerabilities as well. So again, for each of these list of the top 10 in the OWASP, there's kind of the high level description. There's some examples of what it means, in this case, to have broken access control, and then some either general or potentially more specific guidelines for what one can do to prevent those from occurring. So, for example, in this application, scenario 1, an application uses unverified data in a SQL call that is accessing account information, where as part of the processing, we take the parameter from the URL. Remember, we had a question mark name equals Steve. In this case, we have a parameter called account. So the idea is that the actual account information is encoded directly in the URL parameters themselves. That is less common. That used to be extremely common in the design of web applications. And then whatever is provided in terms of that account is what is then used to execute the database query associated with that account. In that scenario, an attacker just takes the URL, takes the parameter string associated with that URL, and just modifies it. Probably won't work in a bank account these days, but will still work in all sorts of various things. Now, again, we talked about this a little bit, right? How we learn these important techniques in this class. I think maybe some of them are obvious, some of them you're already aware of, others are maybe new to you, and this seems harmless, right? This kind of exploration. Okay, I take an account parameter, I see it in the URL, and I'm just going to change it and see what happens. Exercise caution when doing that, right? That in some circumstances, certainly when it's been done in sort of an automated way, has been considered violations of various federal guidelines and laws regarding quote unquote hacking. So playing around with it and seeing what happens is probably okay. Maybe then notifying the web application developer that you have a serious vulnerability is probably where you need to stop at that point. It will not be that obvious, but that type of vulnerability still exists in applications today. Separately, where it's just directly sort of a security through obscurity of having target URLs associated with more or less privileges on a system, just by finding or navigating to those URLs, provide that additional information or additional access that was not supposed to be provided. Those are both pretty serious vulnerabilities in the design of your access control in a system. But as we were to look at various CVEs or various bug bounties that gets claimed in the corresponding already patched CVEs, it's not going to be that obvious. But things of that nature still occur quite a bit. There's a reason this is listed as number 1 in that top 10 list of things you have to watch out for when designing a web application. So in terms of preventing it, this is pretty general advice, so it's a little bit hard to act on until you're in the process of designing something. But deny by default is a good policy in the first place. Don't assume certain permissions will be in place. Actually implement those policies associated with access control. Another big kind of related vulnerability that is becoming less of an issue, but it still exists, is making sure that metadata, unintended metadata, is not publicly available. A .git folder provides a little bit of information about the developer access to your web application, but there's other metadata that could include secrets that we looked at earlier in the semester that you want to make sure never actually gets published. Logging and actually being able to provide that sort of Um, Process and procedures for alerting when those type of automated attacks are happening is an important thing, and potentially, providing rate limits to various accessing of resources. If there's a reason to expect that this particular admin page should only be accessed once a day or something like that, and you're seeing hundreds of requests to it, there's a reason for that generally, and you can provide rate limiting for particular resources. Those are all pretty, I would say, hard to act on suggestions. Another way to think about that is when designing your application, you have to be thinking about access control. And maybe starting with number one is a good starting place, that we have users, they should have as little access as possible. And we have authentication-based mechanisms for providing additional access to users. We're not just hiding it via parameters or via URLs that are only available to certain users. Number two is cryptographic failures, both kind of blatant cryptographic failures of just not using well-known cryptographic approaches, or using maybe more dated cryptographic approaches versus current state of the art. That has to do with just the sensitive data, the confidential data you may have in your system, things like passwords and credit card data and the like. Now, we talked a little bit about this, and we don't really go into too much more details. One, building a modern web application today, having anything to do with user information, which tends to be most interesting web applications, has to be aware of various, national, international, even state level regulations, like GDPR. Every website you go to that has that annoying pop-up that says, "Please let us, store as much information as possible," that is their ham-fisted attempt to kind of comply with GDPR regulations. If you're doing anything with regards to payment information, there are pretty comprehensive standards one has to follow for how that information gets stored and processed. In that sense, your best bet is to use existing frameworks that claim and audit compliance to those standards. Certainly, if you're in the process of developing your own framework, you have to be aware highly, very much of those standards. So you have to worry about what data is going to be in clear text in your system, both external to the application, internal to the application. Are you happening to use kind of old or weak cryptographic algorithms or protocols, either kind of by default or as fallback options here? Are you using older hash functions versus what's considered stronger, more resistant to the type of rainbow table and other hash-based attacks we talked about last week? This is, again, is kind of a difficult one to guarantee you are doing properly. That's why these kind of standardization approaches are being made. That's why it's becoming, right, a legislative issue, is that it is really hard to ensure this. We attempt to set those standards. And so your attempt is really more to prevent these. Your goal is to really adhere to existing standards here. For example, if you're encrypting your credit card information, but then when retrieved, you automatically decrypt all that data. If you had any sort of other database flaw in your system, then perhaps credit card numbers could be revealed in plain text. If you have a site that doesn't enforce HTTPS for all pages or supports fallback options from HTTPS, then you have all the issues associated with plain text HTTP traffic, that it can be intercepted. Depending on what you're sending over that clear text HTTP traffic, that can be a big issue with regards to personally identifying information, things like credit card information, logins, and things of that nature. And then the same kind of issue we were talking about with regards to storing passwords, we were talking about how Linux stores passwords and how Windows stores passwords, and we're playing around with that in the lab. Every application potentially has its own database, has its own users. It would not be using the OS's own mechanisms for taking care of those passwords. It would need to have its own separate mechanism, typically through a database, for securing those passwords, securing those logins. You wouldn't want your users of your site to be users on the server itself, so it would have to be a separate thing. All the same kind of issues we were talking about with what older user account authentication techniques were doing. We know those issues now, but there's really no guarantee unless you yourself, as the web application developer, code that yourself or use a framework that requires that. You may be kind of repeating the mistakes of the past with regards to user password storage and retrieval. let's leave things here for today. Thursday, we'll have our quiz. We'll kind of finish up the rest of these. I know it's a little abstract in a sense. I'll try to bring up some examples when we get to the more specific vulnerabilities to see what that looks like in practice, so it feels a little bit more, tangible to you as you're considering these issues.